Tonight, we're going to go inside one of the strangest objects in the known universe. Not a black hole, not a neutron star, but something far more common and in many ways far more unsettling. A white dwarf. A stellar corpse, roughly the size of Earth, but containing the mass of an entire sun, packed so tightly that matter inside it stops behaving the way matter anywhere else does. Electrons refuse to move. Pressure builds without temperature. The normal rules that govern atoms, that govern chemistry, that govern everything you've ever touched or held or seen, simply stop applying. By the end of tonight, you're going to understand why white dwarfs sit at the boundary between the physics we can see and the physics that breaks our intuitions completely, and why what happens inside them might be the closest thing in nature to a fundamental limit on reality itself. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what you know about stars. A star is, at its core, a balancing act. Gravity is always trying to pull a star inward, to collapse it, to crush it down into nothing. And the only thing stopping that collapse is the outward pressure of nuclear fusion happening in the star's core. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. The energy released by those reactions pushes outward against gravity's inward pull. For billions of years, those two forces balance each other, and the star holds its shape. Our own sun has been running this balance for roughly 4.6 billion years. It will keep running it for another 5 billion or so. But stars don't live forever. Eventually, the fuel runs out. And when it does, when the fusion reactions slow and then stop, gravity finally wins. The question is, what happens next? For most stars in the galaxy, stars roughly like our sun or smaller, the answer is a white dwarf. Not a dramatic explosion, not a catastrophic collapse into infinite density, but something quieter and stranger. A slow contraction into a state that shouldn't be able to exist, but does, held up by a quantum mechanical effect that has nothing to do with heat or pressure in any ordinary sense. Understanding what a white dwarf actually is requires backing up a little. Because the process that creates one is not simple, and the physics behind how it survives is bizarre in ways that take time to absorb. A star like our sun spends most of its life on what astronomers call the main sequence. That's just a name for the stable phase where hydrogen fusion dominates the core. Our sun sits comfortably on the main sequence right now, converting about 600 million metric tons of hydrogen into helium every single second. That number is not a typo. 600 million metric tons per second. And it has been doing this for 4.5 billion years without running out of hydrogen, because the sun is enormous enough to have started with an essentially incomprehensible supply. But even that supply is finite. After roughly another 5 billion years, the hydrogen in the sun's core will be largely depleted. The core will be mostly helium, which doesn't fuse under the same conditions as hydrogen. Without fusion, there's no outward pressure from the core. Gravity, always patient, begins to win. The core contracts. And here's where things get interesting. As the core contracts, it heats up. The outer layers of the star, still rich in hydrogen, begin to expand outward. The star puffs up enormously. Our sun will swell to perhaps 200 times its current radius, swallowing Mercury, engulfing Venus, and reaching close enough to Earth to transform its surface completely. This is the red giant phase. It's not a gentle swelling. It's a death rattle playing out over hundreds of millions of years. During the red giant phase, the core gets hot enough to ignite helium fusion. Helium fuses into carbon and then into oxygen. This buys the star more time, but not as much time as hydrogen fusion did. Helium burns faster and less efficiently. The respite is shorter. Eventually, the helium runs out too. For a star the size of our Sun, the core never gets hot enough to fuse carbon. Carbon fusion requires temperatures above about 500 million degrees Kelvin, and lower mass stars can't generate that kind of heat even during gravitational contraction. So the star stalls. The core, now mostly carbon and oxygen, contracts further. The outer layers, loosely bound and puffed up from the red giant phase, drift away into space. Over tens of thousands of years, those outer layers disperse into a beautiful expanding shell of glowing gas called a planetary nebula. The name is misleading because these structures have nothing to do with planets. 19th century astronomers, with small telescopes, thought the glowing disks looked like the planets they were used to seeing in their eyepieces. They were completely wrong about what they were looking at, but the name stuck, and we've been using it ever since. Some of these nebulae are among the most beautiful objects in the sky. The Ring Nebula in the constellation Lyra, the Helix Nebula in Aquarius, a vast glowing ring visible even through a pair of binoculars, the Butterfly Nebula in Scorpius, with its enormous winged lobes of gas. All of these are the discarded outer layers of dying stars. All of them have a white dwarf at their center, or will soon. The glowing shells are illuminated by ultraviolet radiation from that hot, newly exposed core. As the nebula expands and dilutes over tens of thousands of years, the gas eventually becomes too diffuse to be visible, and it disperses into the surrounding interstellar medium. What remains is the naked core of the original star, a dense, hot, incredibly compact object roughly the size of Earth, but containing somewhere between 1/2 and 1.5 times the mass of our Sun. That object is a white dwarf. Let that scale settle for a moment. Earth has a radius of about 6,370 kilometers. Our Sun has a radius of about 696,000 kilometers. A typical white dwarf has a radius somewhere around 7,000 kilometers. So you are taking the mass of an entire star and compressing it into a volume only slightly larger than Earth. The density that results from this is extraordinary. A teaspoon of white dwarf material would contain somewhere between 5 and 15 metric tons. The surface gravity of a white dwarf is roughly 300,000 times stronger than Earth's surface gravity. If you somehow stood on the surface of a white dwarf, you would experience forces that would reduce you to a layer thinner than a sheet of paper in a fraction of a second. The atmospheric pressure at the surface is about 100 billion times what you experience standing at sea level on Earth. And the interior is orders of magnitude more extreme than that. The temperatures inside a young white dwarf's core can reach tens of millions of degrees Kelvin. The densities in the interior are around 1 million times the density of water. 1 million times. For context, water has a density of 1 gram per cubic centimeter. The densest material you're likely to encounter in daily life, lead, has a density of about 11.3 grams per cubic centimeter. Osmium, the densest naturally occurring element on Earth, reaches about 22.6 grams per cubic centimeter. A white dwarf interior sits at around 1 million grams per cubic centimeter, roughly 44,000 times denser than osmium. The question that should be forming in your mind right now is what holds it up. If gravity is this strong, and if there's no fusion happening to push back against it, why doesn't the white dwarf just keep collapsing? Why doesn't it crush itself into something even smaller? The answer to that question is one of the most remarkable results in all of physics. And it was worked out in 1930 by a 19-year-old physicist traveling by ship from Madras to Southampton. His name was Subramanian Chandrasekhar. He was on his way to Cambridge to continue his studies, and during the voyage, somewhere in the Indian Ocean, he started doing calculations. He was thinking about what happens to a star when it runs out of fuel. He knew about white dwarfs. Several were known at the time. The companion star to Sirius, known as Sirius B, was a famous example. It had been discovered in 1862, and its extraordinary density had puzzled astronomers for decades. Chandrasekhar also knew about a concept that had been developed a few years earlier, in 1926, by the physicist Ralph Fowler. Fowler had shown that white dwarfs could be supported against gravity, not by thermal pressure, not by heat, but by something called electron degeneracy pressure. This was an entirely new idea, and understanding it requires a detour into quantum mechanics, because electron degeneracy pressure is a purely quantum mechanical phenomenon with no classical equivalent. Nothing in everyday experience prepares you for it. Here is the core idea. In quantum mechanics, particles don't just have positions and velocities the way classical physics describes. They have quantum states. Each quantum state is characterized by a set of quantum numbers, values that describe the particle's energy, angular momentum, and spin. And one of the fundamental rules of quantum mechanics, one of the deepest structural features of the universe, is the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli, who formulated it in 1925. The Pauli exclusion principle says that no two identical fermions can occupy the same quantum state simultaneously. Fermions are particles with half-integer spin. Electrons are fermions. Protons are fermions. Neutrons are fermions. The word fermion comes from Enrico Fermi, one of the physicists who helped develop the statistical mechanics of these particles. The exclusion principle applies to all of them. Now, why does this create pressure? In an ordinary gas, the atoms and electrons are spread out. There's plenty of room. Most quantum states are unoccupied. Electrons can move relatively freely between states because most states are available. But compress matter enough, and something changes. As you force electrons closer together, as you reduce the volume they're confined to, the number of available low-energy quantum states decreases. Eventually, you reach a situation where all the lowest energy states are filled. Every available slot at low energy is occupied. The Pauli exclusion principle then forbids any additional electrons from occupying those states. So the electrons resist being compressed any further. Not because they're bumping into each other in a mechanical sense. Not because of heat. Not because of any force we normally think of as pressure. But simply because the universe does not allow two electrons to be in the same quantum state. This resistance is electron degeneracy pressure. It's a consequence of the fundamental geometry of quantum states, of the structure of the quantum world itself. It is not thermal. It does not come from motion driven by heat. It comes from the sheer impossibility of squeezing particles into already occupied quantum slots. Think about what this means physically. At ordinary densities, electrons have a vast landscape of available quantum states to occupy. They fill only the lowest ones and leave most of the higher states empty. There's room to breathe. If you compress the material, the electrons are forced closer together. They fill more states, but there are still plenty of empty states available at higher energies. But keep compressing, and the available states at any given energy fill up. The electrons have nowhere to go. They can't be pushed into states that are already occupied. The matter resists compression, not because of heat, not because of any classical mechanical resistance, but because the quantum state landscape has run out of room at low energies. This is an entirely new mechanism of pressure that has no analog in anything you've experienced. The physicist Ralph Fowler recognized in 1926 that this mechanism could support white dwarfs against gravity. And it was the right answer. At the densities inside a white dwarf, electron degeneracy pressure is the dominant force opposing gravity. But Chandrasekhar saw a complication that Fowler had missed. At the densities inside a white dwarf, electrons are being compressed into such small volumes that their momenta become enormous. By the uncertainty principle, another fundamental result of quantum mechanics, confining a particle to a smaller space means its momentum must be larger. Large momentum means large velocity. And at white dwarf densities, the electrons are moving at velocities that are a significant fraction of the speed of light. At those speeds, special relativity changes the relationship between energy and momentum. The relativistic version of the relationship between momentum and kinetic energy is different from the classical version. And when Chandrasekhar worked through the relativistic version of Fowler's calculation, the result was disturbing. In the non-relativistic case, where electrons move slowly, degeneracy pressure increases with compression faster than gravity does. Compress the star. Degeneracy pressure wins. The star bounces back. This is what gives the white dwarf its stability. But in the relativistic case, where electrons move at close to the speed of light, the story changes. The pressure still increases with density, but the exponent changes. It no longer increases fast enough relative to gravity. There's a maximum mass for which this mechanism can hold. Above that mass, gravity wins, regardless of how compressed the electrons become. The runaway collapse that follows cannot be stopped by electron degeneracy pressure. Chandrasekhar calculated this maximum mass. He found it to be approximately 1.4 times the mass of our Sun. If a white dwarf exceeds that mass, electron degeneracy pressure cannot hold it up. Gravity wins. The object collapses further. What it collapses into depends on the mass. A neutron star, if the mass is in a certain range. A black hole, if it's high enough. But not a white dwarf. This mass limit is now called the Chandrasekhar limit. It is one of the most important numbers in astrophysics, and it has consequences that reach across the entire observable universe. The British establishment was not welcoming of this result. Arthur Eddington, the most prominent astrophysicist in Britain at the time, publicly attacked Chandrasekhar's calculation at a meeting of the Royal Astronomical Society in January 1935. Eddington believed the result was unphysical. He couldn't accept that stars could collapse to something denser than a white dwarf. He said there must be a natural law that prevents this. That Chandrasekhar had made an error somewhere in combining quantum mechanics with relativity. He hadn't. Eddington was wrong. But the confrontation was devastating for Chandrasekhar professionally. He left Britain and moved to the United States, eventually joining the University of Chicago, where he spent the rest of his career. The scientific community gradually came around to accepting his result over the following decades. In 1983, over 50 years after that calculation on the ship crossing the Indian Ocean, Subramanian Chandrasekhar received the Nobel Prize in Physics. It was a long wait, but the physics was right from the beginning. Now understand what the Chandrasekhar limit actually means for the matter, inside a white dwarf sitting safely below it. Below that limit, electron degeneracy pressure holds. The electrons are pressed into their lowest available quantum states, and the Pauli exclusion principle prevents any further compression. The matter is in a state called degenerate matter. And degenerate matter does not behave like any material you have ever encountered. In an ordinary material, temperature and pressure are closely linked. Heat something up, and the pressure it exerts increases. Cool something down, and pressure decreases. This is captured in the ideal gas law, and it applies to virtually every substance you interact with in daily life. Air in a balloon, water vapor in a steam engine, the plasma at the center of an ordinary star. All of these follow the basic rule that more heat means more pressure, and more pressure means more heat. But degenerate matter breaks this rule completely. The pressure of degenerate matter does not depend on temperature at all. You can heat a white dwarf's interior to 100 million degrees or cool it to near absolute zero, and the electron degeneracy pressure remains essentially the same. This is not a small correction. This is not a nuance. This is a complete and total violation of the relationship that governs all ordinary matter. Temperature and pressure are decoupled. The electrons are in their lowest available quantum states. Adding heat doesn't push them into new states in a way that changes the pressure, because the degeneracy pressure is set entirely by the density and composition, by how many electrons are packed into a given volume, not by how energetic they are thermally. The thermal energy of the electrons contributes to the total energy, but it doesn't dominate the pressure. The quantum mechanical degeneracy, pressure, dominates. And that pressure doesn't care about temperature. This has consequences that take some time to fully absorb. A white dwarf, unlike every other astrophysical object we know of, does not shrink as it cools. Normal objects cool and contract. A hot metal ball shrinks slightly as it loses heat, and the thermal vibrations of atoms diminish. Gas, clouds, cool and condense. But a white dwarf cools without changing size. The degenerate electrons maintain their configuration regardless of temperature. The radius of a white dwarf is determined by its mass and composition, not by its temperature. As it radiates away its heat over billions of years, it just gets dimmer, cooler, but no smaller. This is deeply counterintuitive and yet absolutely true. The size of the object is frozen in by quantum mechanics, not by thermodynamics. And it means something important for how we observe these objects. Two white dwarfs with identical masses and compositions, but completely different temperatures, have essentially the same radius. One might be freshly formed, blazing at 100,000 degrees at the surface. The other might be ancient, cooled to 10,000 degrees after billions of years. They're the same size. The hot one is brighter, the cool one is dimmer, but the radius hasn't changed. It can't. The degenerate electron pressure is not sensitive to temperature. There's another consequence that falls naturally out of this. In ordinary astrophysical objects, more massive stars are larger. Our Sun is larger than a smaller star. A red supergiant is larger than our Sun. Mass and radius tend to increase together. But white dwarfs behave in exactly the opposite way. More massive white dwarfs are smaller. This is a direct consequence of the quantum mechanics of degeneracy pressure combined with gravity. A more massive white dwarf has stronger gravity pulling inward. Stronger gravity compresses the degenerate electron gas more. The electrons are forced into smaller volumes and higher momenta. The equilibrium radius, where degeneracy pressure exactly balances gravity, is smaller for a more massive white dwarf. The more massive the white dwarf, the smaller it is. A white dwarf of half a solar mass has a radius roughly similar to Earth. A white dwarf of 1 solar mass is noticeably smaller. A white dwarf approaching the Chandrasekhar limit at 1.4 solar masses has a radius much smaller still. And at the Chandrasekhar limit itself, the radius goes to 0. The pressure cannot balance gravity at any finite size. This inverse mass-radius relationship is one of the strangest features of degenerate matter and one of the most directly testable predictions of the theory. And it has been confirmed, observationally, in white dwarf systems where both the mass and radius can be independently measured. Chandrasekhar's equations, worked out on a ship in the Indian Ocean in 1930, correctly describe what we measure today with modern instruments. The cooling timescale of white dwarfs is one of the most extraordinary aspects of their existence. White dwarfs form at surface temperatures of around 100,000 to 150,000 degrees Kelvin. Some of the youngest and hottest known white dwarfs have surface temperatures above 200,000 degrees Kelvin. At those temperatures, they radiate intensely in the ultraviolet, emitting more radiation than the eye can see. As they radiate heat into space, the surface temperature drops. But there's no internal energy source maintaining the temperature. No ongoing fusion. The only heat available is the thermal energy stored in the nuclei of the carbon and oxygen that make up the interior. Those nuclei, the carbon and oxygen ions, are not degenerate. They behave classically, like ions in a very dense plasma. Their thermal energy is what gets radiated away as the white dwarf cools. The degenerate electrons themselves don't contribute much to the heat content because their thermal contribution is suppressed by the same quantum mechanics that creates degeneracy pressure. The electrons are in their lowest quantum states, and there's very little room to remove thermal energy from them. So the heat reservoir is primarily the ionic lattice, and it's a substantial reservoir. White dwarfs start with enormous thermal energy stored in those ions, accumulated during the star's life and the formation process. Radiating that energy into space takes a very long time. Models suggest that a typical white dwarf of around half a solar mass, cooling from its initial temperature of around 100,000 degrees at the surface down to around 50,000 degrees, takes on the order of 100 million years. Cooling from 50,000 degrees down to around 20,000 degrees takes several billion years. Cooling from 20,000 degrees down to the temperatures of the coolest known white dwarfs, around 3,000 to 4,000 degrees Kelvin, takes longer than the current age of the universe. The universe is about 13.8 billion years old. No white dwarf anywhere in the universe has had enough time to cool completely. Not even close. Every white dwarf that has ever formed is still radiating heat. Every single one. The universe simply hasn't had the time to cool any of them down to a final cold state. The coldest white dwarfs we've detected the most ancient ones, have surface temperatures of around 3,000 to 4,000 degrees Kelvin, still warm by human standards, still radiating. The faintest known white dwarfs in old star clusters are among the oldest objects we can directly observe in the universe. They've been cooling for 10 to 12 billion years, and they're still warm enough to see. The interior structure of a white dwarf is more complex than the broad picture suggests. Go deep into the interior, moving from the surface inward, and things get stranger at each layer. At the very surface is the atmosphere, a thin envelope of gas ranging from a few hundred meters to a few hundred kilometers in depth, depending on the temperature and composition. This is where the white dwarf's spectral lines form, where light from below is filtered through the atmospheric gas, and absorption features are imprinted at characteristic wavelengths that reveal the atmospheric composition. Beneath the atmosphere, if the white dwarf has hydrogen on its surface, there may be a thin helium layer, a residual remnant of the star's helium-rich zones. Below that lies the bulk interior, mostly carbon and oxygen ions in a sea of degenerate electrons. In young, hot, white dwarfs, this interior is liquid. Not liquid in the sense of water, but liquid in the sense that the carbon and oxygen nuclei are in a state of thermal motion, jostling around each other randomly, like ions in a very dense plasma, with the degenerate electron sea threaded through and around them. This is the liquid plasma phase of the interior. At these temperatures, the Coulomb coupling parameter, which measures the ratio of electrostatic potential energy between neighboring ions to their thermal kinetic energy, is relatively small. The thermal energy dominates, and the ions move around freely. As the white dwarf cools, this changes. The thermal kinetic energy decreases. The electrostatic interactions between neighboring ions become more important relative to thermal motion. The Coulomb coupling parameter increases. At a critical value, the ions begin to arrange themselves into a lattice structure. They crystallize. The transition is predicted to occur at a Coulomb coupling parameter of around 175. Depending on the temperature and density of the material, this crystallization temperature ranges from tens of millions of degrees Kelvin at the high-density center to lower temperatures in the outer regions. A freshly formed white dwarf is hot enough throughout its interior that no part of it is crystallized. As it cools over billions of years, crystallization begins at the center, where density and pressure are highest, and spreads outward as the temperature drops. The crystalline front moves slowly outward through the interior. In the coolest and oldest white dwarfs, the crystalline core extends through most of the interior volume. In white dwarfs of intermediate age, there's a partially crystalline core surrounded by a still liquid outer region. And at the boundary between these two regions, conditions exist that are unlike anything we can study in a laboratory. This crystallization was predicted theoretically decades before it could be confirmed observationally. The theoretical framework was developed in the 1960s and 1970s through careful application of plasma physics and condensed matter theory. The prediction was clear enough. Dense ionic plasmas undergo a liquid-to-solid transition when the Coulomb coupling parameter reaches a critical value. For typical white dwarf compositions and densities, this happens at temperatures of roughly 10 to 50 million degrees Kelvin in the interior. The prediction went unconfirmed observationally for decades, because confirming it required either extraordinarily precise measurements of individual white dwarfs, which was difficult, or large statistical samples of white dwarfs at precisely measured temperatures and luminosities, which required technology that didn't exist until recently. That technology arrived in the form of the Gaia spacecraft, the European Space Agency's astrometry mission launched in December 2013. Gaia was designed to measure the positions, distances, and motions of more than 1 billion stars with unprecedented precision. Among its targets were hundreds of thousands of white dwarfs. When astronomers released the second Gaia dataset in 2018 and began analyzing the white dwarf population in detail, they found something unexpected. In a plot of white dwarf luminosity against color, which is essentially a temperature-luminosity diagram, there was a clustering of white dwarfs at a specific temperature and luminosity that didn't match predictions from smooth cooling models. A distinct pile-up of objects in a narrow range, as if white dwarfs were spending more time at a particular temperature than expected, cooling more slowly through that temperature range than through others. The explanation, published in a landmark paper in 2019, was exactly what had been predicted. As the interior of a white dwarf crystallizes, the phase transition releases latent heat, the same way water releases heat as it freezes. This latent heat adds to the thermal energy available to radiate, partially compensating for the heat being lost from the surface. The white dwarf cools more slowly through this temperature range, spending more time there than elsewhere. The result is a statistical excess of white dwarfs at that temperature in any large population sample. The Gaia data showed this directly, not as a theoretical prediction, as an actual feature of the real observed population of white dwarfs in the solar neighborhood. The interiors of dead stars are crystallizing as the universe watches. And the statistical fingerprint of that crystallization is detectable in the number of white dwarfs at each temperature. The crystallization process introduces a further subtlety that has real consequences for how we use white dwarfs as clocks. Carbon and oxygen don't crystallize at exactly the same temperature under the same conditions. At the densities inside a white dwarf, oxygen has a higher melting point than carbon. Oxygen tends to freeze into the crystal lattice at a slightly higher temperature than carbon. This means the crystalline core that forms first is enriched in oxygen. The oxygen preferentially freezes out, while carbon remains in the liquid phase. The result is that the crystalline core has a higher oxygen fraction than the bulk composition of the interior, and the surrounding liquid region has a higher carbon fraction. Carbon, being lighter, floats slightly outward. Oxygen, being heavier, sinks into the crystal. This redistribution of composition releases gravitational energy. It's a process of chemical differentiation driven by the different melting points of carbon and oxygen under the conditions of degenerate matter. And that gravitational energy, released as the composition rearranges itself, adds heat to the interior. It further slows the cooling. Models incorporating this compositional phase separation suggest that some white dwarfs could be several billion years older than simpler models, which assume a fixed composition throughout, would estimate. This has direct consequences for white dwarf cosmochronology. If white dwarfs cool more slowly than the simpler models predict, then the oldest, coolest white dwarfs we observe correspond to stellar populations that formed earlier than simpler models would suggest. The ages of some of the oldest star clusters, as measured by their white dwarf populations, need to be revised. The physics of how white dwarf interiors freeze affects our estimates of how long ago the first stars formed in our galaxy. A microscopic detail of nuclear plasma physics, the slightly different melting points of carbon and oxygen at extreme density, has consequences for galactic archaeology. The surface layers of white dwarfs tell a different story from the interior, and it's a story that has turned into an unexpected window onto destroyed planetary systems. Most white dwarfs, roughly 80% of all known white dwarfs, are classified as DA white dwarfs. The DA classification comes from a spectroscopic notation where the A indicates the presence of hydrogen absorption lines in the spectrum. Their spectra are dominated by those hydrogen absorption lines and almost nothing else. This seems strange at first. If the white dwarf formed from a carbon and oxygen core, why does it show hydrogen? The answer is gravitational sedimentation. At the surface gravity of a white dwarf, 300,000 times Earth's surface gravity, the process of elements settling by mass is extraordinarily efficient. Any hydrogen remaining in or accreted onto the white dwarf floats to the top because it's the lightest. Helium sinks below hydrogen. Carbon, oxygen, and heavier elements sink below helium. The sedimentation happens on timescales that vary with temperature, but are typically much shorter than the cooling timescale. For hot white dwarfs, heavy elements sink out of the observable atmosphere in days to millions of years. For cooler white dwarfs, the process is slower. But over the billion-year cooling timescale, the sedimentation is comprehensive. The observable surface ends up showing hydrogen on top. Below that is a thin helium layer if the white dwarf formed from a star that retained some helium. Below that, the bulk carbon-oxygen interior. The surface looks like pure hydrogen, even though the majority of the star is carbon and oxygen. This layered structure is a direct consequence of extreme gravity acting on a mixed composition over geological timescales. Then there are DB white dwarfs, which show helium spectra. These are thought to have mixed their surface hydrogen and helium layers through convection during a particular temperature range of their cooling, or to have formed with minimal hydrogen to begin with. DC white dwarfs show no strong spectral lines at all, just a smooth continuum. And then there are the DZ white dwarfs. These are the ones that have upended our understanding of what happens to planetary systems around dying stars. DZ white dwarfs show absorption lines from metals in their spectra. By metals, astronomers mean elements heavier than helium: silicon, calcium, magnesium, iron, oxygen, bound in rock-forming minerals. These elements are detected in the spectra of around 25 to 50% of all white dwarfs, depending on the survey and the temperature range examined. And they shouldn't be there. Given the efficiency of gravitational sedimentation at white dwarf surface gravities, heavy elements should sink out of the observable atmosphere quickly. In hot white dwarfs, calcium sinks below the observable atmosphere in days. Even in cooler white dwarfs, it sinks in at most a few million years. But white dwarfs are billions of years old. If no heavy elements had been added since formation, there should be none visible in any white dwarf that has cooled for more than a few million years. And yet, we see them in vast numbers of white dwarfs. The only explanation that fits the data is continuous delivery. Something is continuously providing heavy elements to the surfaces of these white dwarfs right now. The current understanding, supported by substantial evidence from infrared excesses and direct imaging, is that rocky bodies, asteroids, minor planets, and remnant planetary debris are being scattered into orbits that take them close to the white dwarf. When these rocky bodies get too close, the tidal forces from the white dwarf's intense gravity exceed the material strength holding the body together. The body is shredded, torn into streams of dust and gas that spread out into a disk orbiting the white dwarf within the tidal disruption radius. This disk of debris slowly accretes onto the white dwarf's surface, delivering a continuous supply of rocky material. Silicon, calcium, iron, magnesium, water, carbon, everything that made up the original rocky body ends up in the white dwarf's atmosphere, where we can measure it, where we can identify the elements and their relative abundances. And from those abundances, we can deduce the composition of the accreted body. In some cases, the material has a composition similar to the rocky inner planets of our solar system. In other cases, there are signatures of water-rich bodies, carbonaceous bodies, or differentiated bodies that had their own geological layers before being shredded. White dwarf atmospheres have become a laboratory for planetary geochemistry. By reading the spectral fingerprints in a white dwarf's atmosphere, we can reconstruct what kinds of rocky objects existed in the planetary system around the original star before it evolved and consumed or disrupted its planets. We are, in effect, doing the geology of dead worlds through the filter of a dead star's atmosphere. And what we're finding is that rocky planetary systems appear to be common around stars like our Sun. White dwarf pollution is not rare, it's the norm, which suggests that planet formation happens around most stars and that planetary remnants persist even through the dramatic final stages of stellar evolution. When the star swells into a red giant, scatters or destroys its inner planets, sheds its outer layers, and collapses into a white dwarf, debris from the planetary system endures. And that debris slowly finds its way onto the white dwarf, writing the geological history of a dead solar system in the atmosphere of its dead star. Some white dwarfs oscillate. Not dramatically enough to see with the naked eye, and not in ways that change their size significantly. But they pulsate slightly, brightening and dimming over periods ranging from minutes to hours. These pulsating white dwarfs come in distinct classes based on which temperature range drives the pulsation. D, A, V, white dwarfs, sometimes called ZZ-CT stars after the prototype of the class, pulsate when their surface temperature passes through a range where hydrogen in the atmosphere is partially ionized. D, B, V, white dwarfs pulsate when helium in their atmosphere is partially ionized. GW Virginis stars pulsate when both carbon and oxygen in their hotter, less common atmospheres are partially ionized. The driving mechanism in each case involves the kappa mechanism. Kappa is the variable that represents opacity in stellar physics. When the partial ionization zone in the atmosphere compresses, the opacity increases. More opaque material traps more radiation. The trapped radiation builds up pressure. That pressure pushes the layer outward. As the layer expands, it becomes less dense and more transparent. Its opacity decreases. The trapped radiation escapes, and the layer falls back inward under gravity. The cycle repeats. The oscillation is sustained as long as the white dwarf's temperature keeps the partial ionization zone in a geometry where this driving mechanism can operate. As the white dwarf cools past the critical temperature, the driving stops and the pulsations fade away. This means there's a distinct temperature range, called the instability strip, at which each type of white dwarf pulsates. D, AV white dwarfs pulsate when their surface temperatures are around 10,000 to 12,500 degrees Kelvin. D, B, V white dwarfs pulsate at around 22,000 to 29,000 degrees Kelvin. Outside these ranges, the driving doesn't work efficiently, and the oscillations are damped. What makes these pulsations scientifically valuable is that different oscillation modes probe different depths inside the white dwarf. A white dwarf, like a bell, has natural resonant frequencies. Some of these modes are confined to the surface layers. Others penetrate deep into the degenerate interior. By precisely measuring which frequencies are present in the pulsation pattern and how they're shifted or split by the white dwarf's rotation and magnetic field, astronomers can infer detailed information about the interior structure, the depth and mass of the hydrogen layer, the extent of the helium layer beneath it, the point at which the interior becomes degenerate, the beginning of the crystalline core, the total mass of the star. This technique is called white dwarf asteroseismology. It has been applied to dozens of pulsating white dwarfs and has given us by far the most detailed interior structure information we have for these objects. It's a way of seeing inside a star that you cannot otherwise directly observe. The pulsation pattern is the fingerprint of the interior. One of the most profound implications of the Chandrasekhar limit is what it means for stellar death pathways and how that connects to our understanding of the universe itself. Stars more massive than about 8 times the mass of our Sun don't end up as white dwarfs. They have enough mass to ignite successive stages of nuclear burning after helium. Carbon fusion begins in the core, then neon, then oxygen, then silicon. Each stage produces heavier elements, and each stage runs faster than the previous one, because the energy released per fusion event decreases as you move up the periodic table toward iron. Hydrogen burning sustains a star for billions of years. Carbon burning sustains a massive star for perhaps 1,000 years. Oxygen burning for about a year. Silicon burning for about a day. Iron fusion doesn't occur at all, because fusing iron requires energy input rather than releasing it. Iron is the most tightly bound nucleus. There's no energy profit to be made from fusing it. And so, when an iron core builds up at the center of a massive star, the fusion energy source switches off for the last time. The core is now supported only by electron degeneracy pressure, but the iron core's mass quickly exceeds the Chandrasekhar limit. Electron degeneracy pressure can't hold it. The core collapses in less than a second. The infalling iron nuclei are photodisintegrated by the enormous temperatures, splitting back into protons and neutrons. The protons capture electrons, a process called electron capture, creating neutrons and releasing neutrinos. The core becomes an enormous ball of neutrons, and the collapse halts when neutron degeneracy pressure, the same quantum mechanical mechanism as electron degeneracy pressure, but for neutrons, and the strong nuclear force resist further compression. The core rebounds. The shock wave from that rebound, aided by an enormous outflow of neutrinos from the collapsing core, blasts through the infalling outer layers of the star. The outer layers are ejected, a supernova. The remnant of the collapse is a neutron star, or, if the mass is sufficient, a black hole. For stars like our Sun, none of this applies. They lose enough mass during the red giant and planetary nebula phases to end up below the Chandrasekhar limit. They leave behind white dwarfs. The Chandrasekhar limit, 1.4 solar masses, is the dividing line between these completely different categories of stellar death. Below it, electron degeneracy, pressure holds. The star becomes a white dwarf. Above it, the collapse continues into a neutron star or black hole. This mass threshold, derived by a 19-year-old from quantum mechanics and special relativity, separates the quiet endings of ordinary stars from the catastrophic endings of massive ones. The most dramatic consequence of the Chandrasekhar limit involves what happens when a white dwarf approaches it from below. In many star systems across the galaxy, stars don't live alone. Binary systems are common. Two stars orbiting each other, sometimes separated by enormous distances, sometimes close enough that their fates become intertwined. In some binary systems, one star evolves faster than the other, runs through its fuel, sheds its outer layers, and ends up as a white dwarf while its companion is still on the main sequence, still burning hydrogen. If the companion star is close enough, the white dwarf's gravity can pull material off the companion's outer layers. Hydrogen, mostly. This material spirals inward through an accretion disk, heating as it descends, eventually landing on the white dwarf's surface. The accretion disk itself is luminous. The infalling material converts gravitational potential energy into heat and radiation as it spirals inward. The inner edge of the disk, closest to the white dwarf, reaches temperatures of tens of thousands of degrees. Material from the disk eventually impacts the white dwarf's surface at high velocity. As hydrogen accumulates on the surface of the white dwarf, it gets compressed and heated by the tremendous surface gravity. The temperature at the base of the accumulated hydrogen layer rises. Eventually, if the temperature and density reach the threshold for thermonuclear ignition of hydrogen, the accumulated layer detonates. A thermonuclear explosion on the surface. Billions of times more energetic than any nuclear weapon, but still contained to the surface. The explosion blows away the accumulated hydrogen layer, but leaves the white dwarf itself intact. From Earth, this appears as a sudden dramatic brightening of the star system, sometimes by a factor of 10,000 or more in visible light. This is a nova, not to be confused with a supernova, which is far more energetic and completely destroys the white dwarf. A nova is a surface explosion. The white dwarf survives, and the cycle resumes. Hydrogen accretes, builds up, ignites. Nova. The accretion restarts. Some nova systems recur on timescales of years to decades. Others recur over centuries. In some binary systems, the white dwarf gains more mass from accretion than it loses in each nova explosion. It slowly accumulates mass, creeping toward the Chandrasekhar limit. This process can take hundreds of millions of years in some systems. But when the white dwarf finally approaches 1.4 solar masses, when carbon fusion becomes possible in the degenerate core under those conditions, something completely different happens. To understand what follows, you need to understand one more crucial difference between degenerate matter and ordinary matter. In ordinary matter, temperature and pressure are linked. This linkage acts as a thermostat for nuclear reactions. If you ignite a fusion reaction in a pocket of ordinary gas, the heat released raises the temperature. Higher temperature means higher pressure. Higher pressure means the gas expands. Expansion reduces the density and temperature. Reduced density and temperature slow the fusion reactions. The system regulates itself. Hotspots burn out. Runaway thermonuclear explosions in ordinary matter are actually very hard to achieve because the material actively responds to heating by expanding and cooling, suppressing the runaway. This is how ordinary stars remain stable rather than exploding. But in degenerate matter, pressure doesn't depend on temperature. When carbon fusion ignites in the degenerate core of a white dwarf approaching the Chandrasekhar limit, the heat released doesn't cause the material to expand. The degenerate electron pressure doesn't respond to temperature. The material stays at the same density. The temperature rises. Higher temperature makes the fusion reactions run faster, which releases more heat, which makes the temperature rise further, which makes the reactions run even faster. There is no thermostat, no expansion, no cooling mechanism. The burning front accelerates. In a tiny fraction of a second, a thermonuclear burning front propagates through the entire white dwarf. Some models suggest subsonic burning that transitions to supersonic detonation. Others suggest a detonation that begins subsonic and becomes supersonic later. The details are still debated. But the outcome is not debated. The entire white dwarf, a body roughly the size of Earth, containing the mass of the Sun, detonates throughout its volume. The energy released is approximately 1 to 2 times 10 to the power of 44 joules. That number is essentially meaningless without context. Our Sun, burning steadily for roughly 10 billion years, will radiate a comparable amount of energy in total over its entire life. A-type 1. A supernova releases in seconds what our Sun takes 10 billion years to radiate. The white dwarf is completely destroyed, shredded into expanding clouds of radioactive isotopes, predominantly nickel-56, along with iron group elements and intermediate mass elements synthesized in the explosion. Nothing is left behind. Not a neutron star. Not a black hole. Not even a fragment of white dwarf. Just an expanding cloud of fusion products, enriching the surrounding interstellar medium with heavy elements that future planets, asteroids, and living things may someday be built from. What makes Type 1, a supernovae, particularly remarkable to astronomers is their consistency. Because the explosion always happens at roughly the same mass, near the Chandrasekhar limit, the energy released is roughly the same in every event. There are variations. Not all Type 1, a supernovae, are identical, but there's a relationship between the peak brightness of the explosion and the rate at which the brightness declines afterward. Brighter explosions fade more slowly. Dimmer ones fade faster. This relationship, known as the Phillips relation, discovered by astronomer Mark Phillips in 1993, allows astronomers to calibrate any individual, Type 1, a supernova. Measure how fast the brightness declines, and you can calculate how intrinsically bright the explosion was. Once you know how intrinsically bright it was, and you measure how bright it appears from Earth, you can calculate the distance. Type 1. A supernovae are bright enough to be seen from billions of light-years away. This turns them into extraordinarily precise distance indicators, standard candles, in astronomical terminology. In the mid to late 1990s, 2 independent research teams were using Type 1, a supernovae, to measure the expansion of the universe. The Supernova Cosmology Project, led by Saul Perlmutter, the High Redshift Supernova Search Team, led by Brian Schmidt and Adam Rias. Both teams were measuring the distances to Type 1, a supernovae in very distant galaxies, and comparing those distances to the recession velocities of the galaxies. If the universe's expansion had been decelerating since the Big Bang, as was generally expected because gravity should slow it down, the distant supernovae should be slightly closer than expected. both teams found the opposite. The distant supernovae were fainter than expected, farther away than they should be. The universe was not decelerating. It was accelerating. Something was driving the expansion faster and faster. Something that operated throughout the universe, opposing gravity on cosmic scales, pushing everything apart with increasing force. That something had no name and no explanation. It was called dark energy, a placeholder for something physicists still don't understand at a fundamental level. Dark energy appears to constitute about 68% of the total energy content of the universe. It is the dominant component. And we discovered it because of white dwarfs. Because of the Chandrasekhar limit. Because of the physics of degenerate matter and its inability to thermally regulate a thermonuclear reaction. The discovery earned Perlmutter, Schmidt, and Ries the Nobel Prize in Physics in 2011. Dark energy is now one of the deepest unsolved problems in all of science. And the thread that leads to its discovery runs back through Type 1, a supernovae, through white dwarfs exceeding the Chandrasekhar limit, through the physics of degenerate matter, to a young physicist calculating in a ship's cabin on the Indian Ocean in 1930. White dwarfs have magnetic fields, and in some cases, those fields are extraordinary. Earth's magnetic field averages around 40 to 50 microtesla at the surface. The strongest sustained magnetic field ever created in a laboratory is around 45 Tesla, about 1 million times stronger than Earth's field. Many white dwarfs have surface magnetic fields measured in tens to hundreds of millions of Tesla. The most strongly magnetized white dwarfs known have fields approaching 1 billion Tesla. These are called strongly magnetic white dwarfs, or, in the older literature, magnetic white dwarfs. They represent somewhere between 10 and 20% of all known white dwarfs, depending on how the survey is conducted and what field strength counts as magnetic. How do fields this strong come to exist? The basic answer is compression. The magnetic field of a white dwarf is inherited from the field of the original star. When a star's core collapses during the formation of the white dwarf, the magnetic field lines are frozen into the conducting plasma by ideal magnetohydrodynamics. As the plasma contracts and the volume decreases, the same field lines thread through a smaller area. Field strength is inversely proportional to the area they thread through. Compress the volume by a factor of 1 million, and the field strength increases by roughly a factor of 1 million. If the original star had even a modest magnetic field of a few Tesla, compressing it into a white dwarf could produce surface fields in the range of millions of Tesla. But the story doesn't end there. Observations have revealed something puzzling. The fraction of white dwarfs with strong magnetic fields appears to increase as the white dwarfs cool and age. Younger, hotter white dwarfs show lower magnetic incidence. Older, cooler ones show higher incidence. This is inconsistent with a simple relic field that doesn't change with time. Something must be generating or amplifying magnetic fields in aging white dwarfs. The leading hypothesis involves a convective dynamo. As a white dwarf cools and the non-degenerate liquid ionic interior above the crystalline core undergoes convection, the convecting conducting ions can generate and sustain a magnetic field through dynamo action. The same physical process that generates Earth's magnetic field in our liquid iron outer core. If this is correct, then white dwarfs are more dynamically active than their quiet, cooling image suggests. Inside the apparently static exterior, liquid conducting plasma is circulating, driven by the temperature gradient between the hot interior and the cooler surface. And that circulation is amplifying and sustaining a magnetic field. The white dwarf is behaving like a planet, complete with a magnetic dynamo powered by internal heat. Only the interior is a degenerate quantum fluid, and the planet-sized body contains the mass of the Sun. In binary systems, a strongly magnetic white dwarf creates conditions that are among the most extreme in nature. When an intensely magnetic white dwarf is accreting material from a companion star, the magnetic field restructures the entire accretion geometry. In ordinary, non-magnetic accreting white dwarfs, infalling material forms an accretion disk. The disk is a flat, rotating disk of material that slowly spirals inward, losing angular momentum and descending toward the white dwarf's surface. But a strong magnetic field, one that extends far enough into the surrounding space, overwhelms this disk geometry. The magnetic field's pressure exceeds the ram pressure of the infalling material at a distance called the magnetospheric radius. Inside this radius, the infalling material can no longer cross field lines. It has to follow them. The material is channeled, funneled along the magnetic field lines, directed to fall almost straight down onto the magnetic poles of the white dwarf. Two narrow columns of plasma raining down on the polar regions at velocities of thousands of kilometers per second. The kinetic energy of that infalling material is enormous. When the column hits the white dwarf's surface, it decelerates in a standing shock wave. The kinetic energy is converted almost entirely into radiation, mostly X-rays. The temperature in the shock zone reaches hundreds of millions of degrees. The white dwarf's rotation sweeps this X-ray beam around like a lighthouse, modulating the observed luminosity of the system at the white dwarf's spin period. These systems are called polars, or AM Hercules systems, after the brightest member of the class. They were discovered in the late 1970s and have been studied intensively ever since. The magnetic field is strong enough in these systems that it also affects the polarization of light emitted in the accretion region. Cyclotron emission from electrons spiraling along field lines produces strongly polarized radiation that rotates with the system. Measuring the polarization gives direct information about the magnetic field geometry. It gives you a map of the field structure. And in the most strongly magnetic polars, the field is intense enough that it changes the structure of atoms themselves. In a magnetic field of 1 billion Tesla, the Landau levels into which electrons fall in the presence of a field are so widely spaced in energy that hydrogen atoms are stretched into elongated cylindrical shapes along the field direction. Ordinary atomic structure breaks down. The spherical orbitals of normal atomic physics are replaced by cylindrical wave functions aligned with the field. This is not a theoretical prediction that's hard to test. It produces detectable spectral features. The absorption lines of hydrogen in a 1 billion Tesla field are completely different from the absorption lines of hydrogen in no field. The spectrum looks like nothing from normal hydrogen. It looks like an alien element. Until you solve the quantum mechanics of hydrogen in extreme magnetic fields and see that the features match. This was actually a puzzle for a while. Some white dwarf spectra in the early observations of magnetic white dwarfs showed features that looked like no known element. Eventually, the quantum mechanics of atoms in extreme fields was worked out in enough detail to match those mysterious features to hydrogen and helium in fields of hundreds of millions of Tesla. The mystery was solved. But It required developing quantum electrodynamics for conditions that exist nowhere in a laboratory, only at the surface of the most intensely magnetic stellar remnants in the universe. Look up at the night sky on a clear night and find the brightest star. If you're in the northern hemisphere, that's Sirius. Blazing blue-white near the horizon in winter, in the constellation Canis Major. Sirius is the brightest star in the night sky by a comfortable margin, nearly twice as bright as the next brightest star, Canopus. It lies at a distance of about 8.6 light-years, one of the closest stars to our Sun. But Sirius is not one star. It's two. The brilliant blue-white one you see is Sirius A, a main sequence star, about twice the mass of our Sun, in the middle of its stellar life, burning hydrogen in its core. Orbiting it is Sirius B. Sirius B is a white dwarf. It has roughly the mass of our Sun, compressed into a volume about the size of Earth. Its surface temperature is around 25,000 degrees Kelvin, hotter than Sirius A. Hot enough to be classified as a blue-white star. But it's so small, so much smaller than Sirius A, that its total luminosity is less than 0.25% of Sirius A's. The tiny size more than cancels out the high temperature. Sirius B was the first white dwarf to be identified, and its identification came through a chain of reasoning and observation that took decades. Friedrich Bessel in Königsberg was carefully measuring the position of Sirius against background stars over a long baseline of observations in the 1840s. He noticed something. The position of Sirius was not moving in a straight line. It was wobbling, deviating slightly from the smooth, proper motion path it should follow if nothing was pulling on it. Bessel recognized this as gravitational perturbation. Something massive was orbiting Sirius, pulling it back and forth as it moved. But he couldn't see it. Bessel passed in 1846, never having seen the companion. In January 1862, the American telescope maker Alvan Graham Clark was testing a new, roughly 47-centimeter refracting lens, the largest in the world at the time, on the night sky. He pointed it at Sirius, and just a few arc-seconds away from the brilliant star, he saw it. A faint point of light. Sirius B. The invisible companion made visible for the first time. When astronomers worked out the orbit, they found that Sirius B had roughly the mass of the Sun. But it was enormously less luminous than the Sun. Far less luminous than any main sequence star with that mass should be. The spectrum was puzzling. In 1915, Walter Adams at the Mount Wilson Observatory measured the spectrum of Sirius B and confirmed it was hot, far hotter than any star of its luminosity should be. The only way to reconcile the high temperature with the low luminosity was a tiny surface area. Then, in 1925, Adams went further. He measured the wavelengths of spectral lines in Sirius B's spectrum and compared them to the same lines measured in a laboratory on Earth. The lines were shifted toward the red end of the spectrum by exactly the amount of general relativity predicted for light climbing out of the gravitational well of an object with Sirius B's mass and estimated size. This was one of the first confirmations of gravitational redshift using an astrophysical object. Light, leaving the intense gravity of Sirius B, loses energy as it climbs outward, and that energy loss shifts the light toward longer, redder wavelengths. The prediction and the measurement matched. A solar mass object, the size of a planet. The densities implied were extraordinary, far beyond anything known at the time. the physics community was skeptical. Eddington himself called the density absurd, and it would remain unexplained until quantum mechanics provided the answer. Today, Sirius B is the nearest white dwarf that we can clearly observe and study. The closest example of degenerate matter in our cosmic neighborhood, just 8.6 light years away, orbiting the brightest star in our night sky, hidden in plain sight for over 60 years, and once understood, revealing entirely new physics. Every year, across the Milky Way, a few white dwarfs form from the final stages of aging stars. Stars that puffed into red giants shed their outer layers and left their cores behind. Those newly born white dwarfs join a population that has been accumulating since the first generation of stars formed in our galaxy. The estimated number of white dwarfs in the Milky Way is around 10 billion, maybe more, depending on what assumptions you make about the initial mass function of stars and the rate of star formation over galactic history. That's 10 billion stellar remnants distributed throughout the galaxy, slowly cooling. The vast majority of them are invisible to ordinary observations. Most white dwarfs are dim enough that only the nearest ones can be studied in detail from Earth. For every white dwarf we can see clearly, there are thousands we can barely detect, and millions we know must exist, but have never directly observed. They're out there, cooling in the dark, drifting through the galaxy. Some are alone, isolated remnants of stars that formed and spent their lives without companions. Some are in binary systems, locked in gravitational embraces with companion stars that are still alive. Some are accreting from companions, accumulating mass, ticking toward the Chandrasekhar limit over millions of years. The full population of white dwarfs encodes the history of star formation in the Milky Way. When we study the coolest, faintest white dwarfs, the ones that have been cooling for the longest time, we're looking at the remnants of the earliest stars. Stars that formed 10 to 12 billion years ago, when the galaxy was young and still assembling itself from the cosmic gas and dark matter that accumulated after the Big Bang. Those ancient white dwarfs have been cooling ever since. By measuring how cool and dim the oldest white dwarfs are, and knowing the cooling rate from models, we can determine when those stars formed. White dwarf cosmochronology. Stellar archaeology done with dead stars rather than living ones. This approach has given ages for the oldest components of the Milky Way, consistent with ages derived from completely independent methods. The thick disk of the Milky Way is about 10 billion years old, based on white dwarf cooling ages. The halo is 12 billion years old or older. These ages are consistent with the age of the universe, roughly 13.8 billion years. They're consistent with ages derived from the oldest globular clusters. They're consistent with the age of the chemical elements as inferred from radioactive decay. Everything fits. And some of that consistency comes from counting and measuring the cooling states of stellar remnants. There is, finally, a question that white dwarf physics forces you to ask, and it's not entirely abstract. If most stars end as white dwarfs, and if white dwarfs cool so slowly that none in the observable universe has fully cooled, and if the universe continues to expand and eventually runs out of new star formation, then the long-term future of the universe includes an enormous population of slowly cooling white dwarfs. Stellar activity, the burning of hydrogen into helium and heavier elements in stellar cores, is not a process that can continue forever. Stars form from interstellar gas. The supply of gas that can be made into new stars is finite. Star formation is already declining in the Milky Way compared to its peak billions of years ago. On timescales of a few trillion years, most star-forming gas will have been used up. New stars will cease to form. The existing stars will burn out. The most massive will explode and leave neutron stars and black holes. The majority will slowly fade into white dwarfs, and those white dwarfs will cool. Over 100 billion years, over 1 trillion years, over 10 trillion years. Still cooling, still dim, getting dimmer. Eventually, on timescales truly beyond comprehension, they will stop radiating. They will reach thermal equilibrium with the surrounding universe. They will be dark, cold, crystalline bodies drifting through an enormously expanded, cold, dark space. These are the black dwarfs, the hypothetical final state of white dwarf evolution. And they don't exist yet. Not one. The universe is only 13.8 billion years old. The cooling time to reach temperatures where a white dwarf would be truly dark and cold is many trillions of years. The black dwarfs are coming. They're the future endpoint of most stellar matter. But the universe isn't nearly old enough for them to have arrived. In 5 billion years, our own sun will become a white dwarf. The details are complicated, and the fate of Earth during the red giant phase is uncertain. But the fate of the sun is not. It will exhaust its hydrogen. It will swell into a red giant. It will ignite helium fusion in its core. It will shed its outer layers in a planetary nebula. And the core will remain. A white dwarf of roughly 1/2 to 6/10 of the current solar mass. 1,000 times smaller in volume than the sun today. Cooling in the dark where a brilliant star once shone. Whatever planets survive, the red giant phase will orbit this cooling remnant. Their surfaces will receive less and less energy as the white dwarf dims over billions of years. The solar system will slowly go cold and dark. The white dwarf of our sun will be one of tens of billions in the Milky Way by that point. One cooling remnant among billions. And it will cool. Slowly. Over billions of years. Over trillions of years. Crystallizing in its interior. Fading from its white-hot youth to yellow, to orange, to red, to infrared, to silence. That is the future of our star. Not destruction, not annihilation. A quiet crystallization into the dark. What actually happens inside a white dwarf is a story about limits. Limits in physics. Limits in what matter can do. Limits in how far you can push the laws of nature before they produce something that looks like nothing else in the universe. The electrons inside a white dwarf have run out of room. Not room in space. Room in quantum state space. The landscape of available quantum slots is full. And a universe that forbids 2 electrons from sharing a state has nowhere left to put them. So they stay where they are. They hold up a stellar remnant, the size of our planet, against the gravitational pull of a solar mass object. Silently. Without consuming any fuel. Without generating any heat. Just enforcing the most fundamental bookkeeping rule in quantum mechanics. At the same time, the ionic interior is slowly losing its thermal energy. The nuclei, stripped of their electrons and arranged in a crystal lattice, are radiating their heat into space, one photon at a time. The crystal is growing, expanding from the center outward. A phase transition happening inside a stellar remnant, on time scales of billions of years. at temperatures that would vaporize anything on Earth. At the surface, the atmosphere is stratified by extreme gravity into pure layers. Hydrogen on top, heavier elements sinking. And onto that surface, the shredded remains of planetary systems are slowly accreting, delivering the spectral signatures of destroyed worlds. In binary systems, some white dwarfs are pulling material from living companion stars, accumulating mass, moving toward the limit that will unmake them. And in the magnetic ones, field strengths that change the structure of atoms are channeling accreted plasma onto polar hotspots, creating conditions that have no laboratory parallel. All of this in an object the size of our planet. All of this from the same matter that makes up your bones and the air you breathe and the ground you stand on, just pushed into conditions where the ordinary rules quietly step aside and the quantum mechanical scaffolding underneath reality is exposed. There's a phrase in physics sometimes used for cases where a fundamental principle that usually operates invisibly becomes the dominant force. The quantum becomes classical, meaning the strange quantum rules that usually only matter for tiny systems become relevant at macroscopic scales. In a white dwarf, this happens completely. The Pauli exclusion principle, which in ordinary matter just explains why atoms have the structures they have, why you can't pass your hand through a table, why solids are rigid, becomes the force holding up an entire stellar remnant. The quantum is not just relevant. The quantum is everything. The electron degeneracy pressure is not some small correction to otherwise classical physics. It is the only thing standing between the white dwarf and complete gravitational collapse. Everything about the object's stability, its size, its resistance to compression, its immunity to temperature changes, all of it flows directly from the Pauli exclusion principle applied to electrons in a volume the size of a planet. When you see a white dwarf in a telescope, you're looking at quantum mechanics operating at stellar scales. The most basic and fundamental rule of the quantum world, holding up a dead sun. When you understand all of this, when you understand the electron degeneracy pressure and the Chandrasekhar limit, and the crystallizing interior, and the accreted planetary debris, and the magnetic field, and the pulsations, white dwarfs stop looking like ordinary dim stars. They look like something else, like records. Records of everything that happened to a star over its billions of years of life. The composition of the interior reflects the nuclear burning history. The temperature reflects how long it has been cooling. The atmospheric pollution reflects what planetary system surrounded it. The magnetic field reflects the dynamo history of the original star or the convective interior. The pulsation pattern reflects the layered structure of the interior. Every observable property of a white dwarf is a record of something that happened in the star's life, in its death, or in its long cooling afterlife. Reading those records is what white dwarf astronomy is about. And the records are extraordinarily rich. In the cooling curve, a record of stellar formation history. In the atmospheric chemistry, a record of planetary geology. In the magnetic properties, a record of stellar dynamo physics. In the pulsation frequencies, a record of interior structure. White dwarfs are archives, quiet, dim, mostly overlooked compared to the dramatic spectacles of supernovae and black holes, but extraordinarily detailed and extraordinarily common. 10 billion of them in the Milky Way alone. Each one a record of a star that lived and burned and slowly ended. The universe keeps these records in the residual heat of dead suns. And they're still warm enough to read. The next time you see Sirius blazing in the winter sky, remember what orbits it. A companion that contains everything we've been talking about, compressed into a volume the size of Earth. White, hot, still cooling. An archive of physics at a limit. Degenerate electrons refusing to share quantum states. A crystallizing interior. A layered atmosphere sorted by extreme gravity. A record of a star that lived and ended, holding what it knew in a body the size of a planet, cooling slowly in the dark. That's what matter does when you take it all the way to the edge of what physics allows. It stops behaving normally. It becomes something new. And it endures far longer than you would expect anything to endure. The physics inside a white dwarf is not exotic. It's the same physics that governs every atom you've ever touched, just taken further than anything on Earth has ever been taken. And when you see it clearly, when you trace the chain from quantum states to Chandrasekhar's calculation, to dark energy, to the fate of our own sun, something changes in how ordinary matter looks. Everything around you is one set of conditions away from not behaving normally. The quantum scaffold is always there, underneath everything. You just can't usually see it. White dwarfs are where you can. There's a specific technical detail about how white dwarfs form that rarely gets discussed, and it matters for understanding what they actually are structurally. When a star sheds its outer layers during the planetary nebula phase, what remains is not immediately a stable white dwarf. It's a very hot, very dense stellar core that is still contracting. The newly exposed core has surface temperatures that can exceed 150,000 degrees Kelvin, sometimes much more. At this point, it's classified as a pre-white dwarf, a transitional object still contracting toward its final degenerate state. As it cools and contracts further over tens of thousands of years, it reaches the conditions where electron degeneracy pressure halts the contraction entirely. The object settles into its final equilibrium radius. The contraction stops, and the white dwarf is born. From this point on, the radius doesn't change. Only the temperature does. This is a remarkable moment in stellar evolution. A star that spent billions of years changing, growing, pulsating, losing mass, changing its internal structure, finally settles into an unchanging size. Its future is written entirely in how slowly it loses heat. Nothing else determines what happens next. No more evolutionary complexity, just cooling. The birth of a white dwarf is, in a sense, the point at which stellar evolution stops and becomes astrophysical thermodynamics. From birth to final darkness is nothing but the slow release of stored thermal energy, mediated by the physics of degenerate matter and the quantum mechanical crystal forming inside. Billions of years reduced to a single physical process: heat leaving a cooling body. But what a body! The spectral classification system for white dwarfs deserves more attention than it usually gets, because it reveals an intricate evolutionary picture. The classification uses a prefix D for degenerate, followed by letters indicating the spectral features. D. A white dwarfs show only hydrogen Balmer lines. These are transitions of hydrogen electrons between energy levels, producing absorption features at characteristic wavelengths in the visible spectrum. The Balmer series produces lines at 656 nanometers, 486 nanometers, 434 nanometers, and so on, getting closer together toward the ultraviolet. In a hot D, a white dwarf, these lines are broad and strong. As the white dwarf cools, the lines change shape. At around 50,000 degrees Kelvin, the hydrogen in the atmosphere is nearly fully ionized, so there are few neutral hydrogen atoms to absorb light. The Balmer lines are weak. As the temperature drops to around 20 to 30,000 degrees, the neutral hydrogen fraction increases, and the Balmer lines strengthen dramatically. This is the temperature range where A white dwarfs are easiest to study spectroscopically. Below about 5,000 degrees Kelvin, hydrogen becomes fully neutral again, and the Balmer lines weaken and eventually become undetectable in the optical. Cool white dwarfs in this temperature range become DC white dwarfs, showing no prominent absorption lines in the visible, even if they're compositionally similar to D, a white dwarfs. The appearance changes not because the composition changes, but because the temperature determines which spectral features are active. DB, white dwarfs, show neutral helium lines. The helium in their atmospheres is visible in the temperature range of roughly 12,000 to 40,000 degrees Kelvin. Outside that range, the helium is either too ionized or too neutral to show prominent features in the optical. The spectral classification also includes numbers indicating the temperature of the white dwarf. These numbers run from 2 to 9, representing a temperature range from above 50,000 degrees down to about 5,000 degrees Kelvin. So, a D, a 2 white dwarf, is a hydrogen atmosphere, white dwarf with a temperature around 50,000 degrees. ADA, 9 is a hydrogen atmosphere, white dwarf, cooling toward 5,000 degrees. This classification system, seemingly arcane, contains a wealth of information. Reading the spectral type of a white dwarf tells you immediately about its atmospheric composition, its temperature range, and what physical processes are likely operating in its surface layers. It's a compact encoding of the most important observable properties developed over decades of spectroscopic observation of thousands of white dwarfs. One of the most interesting populations in the study of white dwarfs is what happens when 2 white dwarfs are in a binary system together. Double white dwarf systems are not rare. Many binary stars evolve at similar rates if their masses are similar enough, or in systems with particular initial configurations, and both members can end their main sequence lives within a few billion years of each other. The result is 2 white dwarfs orbiting each other. Double white dwarf binaries are fascinating for several reasons. First, they radiate gravitational waves. Any 2 massive objects orbiting each other radiate energy in the form of gravitational radiation according to general relativity. For most binary stars, this energy loss is negligible. The orbit barely shrinks over the age of the universe. But for compact objects, like white dwarfs in tight orbits, the gravitational wave energy loss can be significant. A pair of white dwarfs in a tight orbit slowly spiral together as they radiate gravitational waves. The orbit shrinks. The orbital period gets shorter. The 2 white dwarfs get closer. Eventually, if the orbital evolution continues long enough, the less massive white dwarf fills what's called the Roche lobe, the region around each star where its gravity dominates. When the smaller white dwarf fills this lobe, material begins to flow from it onto the larger white dwarf. The system becomes an accreting double white dwarf binary. What happens next depends on the masses involved. In some cases, stable mass transfer occurs, and the system settles into a relatively stable configuration. In other cases, depending on the mass ratio, the mass transfer is dynamically unstable. The smaller white dwarf can be tidally disrupted, shredded by the gravity of the larger one. And in some configurations, particularly when the total mass exceeds the Chandrasekhar limit, the system can lead to a Type 1, a supernova. Double white dwarf mergers are one of the proposed channels for creating Type 1, a supernovae, in addition to the white dwarf accreting from a normal star scenario we discussed earlier. In double white dwarf systems, with orbital periods of hours or even minutes, the gravitational wave emission is strong enough that future space-based gravitational wave detectors should be able to measure it directly. The Laser Interferometer space antenna, known as LISA, planned for launch in the 2030s, will be sensitive to gravitational waves in the millihertz frequency band. Double white dwarf binaries emit gravitational waves at exactly these frequencies. LISA is expected to detect tens of thousands of double white dwarf binaries throughout the Milky Way. It will see them as individual sources, providing a census of these systems in our galaxy that ground-based telescopes can barely begin to compile. Some of the brightest gravitational wave sources for LISA will be specific double white dwarf binaries already known from optical surveys. Verification binaries, they're called. Systems where both the gravitational wave signal and the orbital properties from optical observations can be cross-checked. These systems will serve as calibrators for the LISA detector, and they'll give us the most precise tests yet of general relativity in the regime of compact binary evolution. Double white dwarfs are gravitational wave sources. The universe is already broadcasting signals from them. We're building the instrument to hear it. The relationship between white dwarfs and neutron stars is more than just a comparison between two types of stellar remnant. They represent two different ways the universe solves the same problem: how to support matter against gravity when there's no nuclear energy source. In a white dwarf, the solution is electron degeneracy pressure. Electrons, being fermions, refuse to share quantum states. The resulting pressure supports the white dwarf against gravity up to the Chandrasekhar limit. In a neutron star, the situation is more extreme. When a stellar core collapses beyond the Chandrasekhar limit, electrons are forced into protons, creating neutrons. The neutrons themselves are fermions. They also obey the Pauli exclusion principle. At neutron star densities, neutron degeneracy pressure takes over the role that electron degeneracy pressure played in the white dwarf. A neutron star is, in a sense, a more extreme version of the same quantum mechanical mechanism, but at densities so high that the strong nuclear force which governs the interactions between protons and neutrons at sub-femtometer distances becomes relevant. The interior of a neutron star is governed by nuclear physics rather than atomic physics. The matter has been compressed beyond the atomic scale entirely. Nuclei are no longer recognizable as nuclei. It's a dense fluid of hadrons, particles made of quarks, interacting through the strong force, and the densities are so extreme at the center of a massive neutron star that the strong nuclear force alone may not be sufficient to hold the star up. The neutron degeneracy pressure, combined with the repulsive core of the nuclear interaction, provides the support. But if the neutron star's mass exceeds roughly 2 to 3 solar masses, depending on the equation of state of dense nuclear matter, which is still an active research area, the support fails. Gravity wins again. The neutron star collapses into a black hole. The white dwarf, the neutron star, the black hole. 3 different endpoints. 3 different ways matter behaves when compressed beyond ordinary conditions. The white dwarf is where ordinary matter, pushed hard enough, stops behaving normally, but doesn't yet leave the realm of atoms and electrons. The neutron star is where atoms are left behind and nuclear matter takes over. The black hole is where even nuclear matter can't hold out, and space-time curvature becomes so extreme that nothing can prevent collapse. Each threshold, the Chandrasekhar limit for white dwarfs, the Tolman-Oppenheimer-Volkoff limit for neutron stars, is a point where one set of physical rules fails to sustain equilibrium, and gravity takes matter to a new regime. These thresholds are not arbitrary numbers. They emerge from specific physical principles, from the quantum statistics of fermions, from the nuclear force, from general relativity. They tell you something deep about the structure of the laws of physics, about how matter can fight gravity and how gravity eventually wins. White dwarfs, standing at the first of these thresholds, are where you can most directly see the quantum mechanical foundation of matter's resistance to gravity. Because the densities are extreme but not nuclear. Because the matter is still made of recognizable electrons and nuclei. Because the quantum mechanics is the Pauli exclusion principle, which you can understand without invoking the strong nuclear force or quantum chromodynamics. The physics is accessible. The numbers are extraordinary. And the object is real. There is a specific experiment that is, in a sense, run continuously by nature and that bears directly on the physics of white dwarfs. It's an experiment about what happens to ordinary matter under extreme pressure. In a laboratory, we can achieve enormous pressures by using diamond anvil cells, devices that focus the force of a hydraulic press onto a tiny sample of material through 2 opposing diamond tips. Diamond anvil cells can achieve pressures of around a few million atmospheres, a few hundred gigapascals. At these pressures, ordinary metals start behaving strangely. Hydrogen, normally a gas, becomes a solid. Under sufficient pressure, hydrogen may become metallic, conducting electricity like a metal, because the electrons are squeezed so close together that they become delocalized. This metallic hydrogen is thought to exist in the interiors of Jupiter and Saturn, where pressures reach tens of millions of atmospheres. At higher pressures still, solid materials transform into new crystal structures. Iron at extreme pressures has a different crystal structure than iron at ordinary pressure. The periodic table of elements doesn't change, but the arrangements of atoms into crystals change under pressure. And at higher pressures than any laboratory has achieved, theory predicts further changes. Electron shells begin to overlap in ways they don't at normal pressure. Chemical bonds change character. At pressures 1 billion times greater than atmospheric pressure, matter begins to approach conditions found in white dwarf interiors. And at that point, the laboratory model breaks down. We don't have instruments that can probe matter at those pressures. We don't have materials that can confine matter under those conditions. The experiments can't be run in a laboratory. But nature runs them. Inside white dwarfs. Inside neutron stars. Inside the cores of giant planets. These astrophysical objects are, in a real sense, physics experiments that we can observe from a distance but cannot reproduce. The white dwarf is the experiment that tells us what happens when you take ordinary atomic matter and compress it by a factor of 1 million in density. when all the empty space inside atoms is squeezed down. When the electrons that once occupied wide, loosely bound orbitals around nuclei are pressed so close together that the Pauli exclusion principle becomes the dominant interaction. What happens is degeneracy. The quantum mechanical state of the matter transforms, and the observable consequences, the size, the cooling rate, the pulsation pattern, the magnetic field, the spectral composition of the atmosphere, are what we detect from light years away and use to test our understanding of physics at extremes we can never reproduce. Every white dwarf we study is a data point from an experiment we couldn't design, one that nature has been running continuously for billions of years. It's also useful to think about the energy scales involved in white dwarfs, because they give you a concrete sense of what degenerate matter actually means. In ordinary matter, the thermal energy of atoms and electrons at room temperature is a few hundredths of an electron volt. The ionization energy of hydrogen, the energy required to strip an electron from a hydrogen atom, is about 13.6 electron volts. Chemical bonds typically involve energies of 1 to 10 electron volts. These are the energy scales that govern ordinary chemistry and thermal physics. In a white dwarf, the energy scale of the degenerate electrons is enormously larger. The Fermi energy, which is the energy of the highest occupied electron state in the degenerate sea, is in the range of tens of thousands of electron volts for typical white dwarf interior conditions. That's roughly 1,000,000 times larger than the thermal energy of electrons at room temperature. What this means is that the quantum mechanical energy of the electrons completely dominates over their thermal energy. Even if the interior of the white dwarf is at a temperature of 10 million degrees Kelvin, which corresponds to a thermal energy of around 900 electron volts per particle, this is still much smaller than the Fermi energy of tens of thousands of electron volts. The electrons don't care about the temperature. Their behavior is determined by their quantum mechanical state, not by their thermal motion. This is what it means for matter to be degenerate. The quantum energy scale dominates over the thermal energy scale, and the pressure that results, the electron degeneracy pressure, is similarly enormous compared to what thermal pressure could provide at the same temperature. If you tried to support a solar mass of matter against gravity using only thermal pressure, you would need temperatures of billions of degrees throughout the interior. Stars do something like this, in a dynamic way, constantly replacing the heat lost from the surface through ongoing fusion. But a white dwarf has no fusion. It relies entirely on degeneracy pressure. The quantum mechanical state of the degenerate electron sea, characterized by the Fermi energy, provides the pressure that a thermal plasma would require billions of degrees to provide. The quantum takes the place of heat, and unlike heat, it doesn't have to be continuously replenished. It doesn't run out. It's not consumed. It's just there. As long as the matter remains compressed and the Pauli exclusion principle remains a rule of the universe, which, as far as we can tell, it does. Permanently. Return to the very basic question this story started with. What happens when matter stops behaving normally? The answer inside a white dwarf is, it finds a new normal. Not chaotic, not disordered. A different mode of existence entirely. Stable, predictable, governed by the same laws of physics, but by different aspects of those laws than dominate in ordinary conditions. The electron degeneracy that holds a white dwarf together is not a quirk or an anomaly. It's the most direct expression of quantum mechanics you can find at macroscopic scales. The Pauli exclusion principle, usually invisible in everyday life, because matter at ordinary densities is far from degenerate, comes forward completely. It becomes the structure of the object. And because the Pauli exclusion principle doesn't depend on temperature, the white dwarf achieves something ordinary matter cannot: true thermal independence of its pressure. It can cool without changing. It can exist as a stable equilibrium regardless of its thermal state. Ordinary objects burn, or cool, or collapse. White dwarfs persist. They radiate away their heat over billions of years and remain structurally unchanged. They crystallize their interiors over billions of years and remain the same size. They accumulate planetary debris over billions of years and simply incorporate it into their surfaces. They exist in a state that is as close to eternal as anything made of ordinary matter can achieve. Not truly eternal. On sufficiently long timescales, even white dwarfs change. They cool. They crystallize completely. They become black dwarfs, cold and dark, and on timescales that make the age of the universe seem like a heartbeat. Even the matter in black dwarfs may slowly transform through quantum tunneling and proton decay, if those processes exist. But on any timescale that a civilization of thinking beings has ever contemplated, white dwarfs persist. They endure. They hold their shape. They hold their records. They hold the physics of their interiors unchanged, waiting to be read by anyone with the instruments and the understanding to read it. We have the instruments. We have most of the understanding. And we're still learning. The physics inside a white dwarf is not fully solved. The equation of state of dense carbon-oxygen matter at megapascal pressures. The detailed dynamics of crystallization and phase separation. The mechanism of magnetic field generation in cooling white dwarfs. The precise conditions under which double white dwarf mergers produce type 1, a supernovae, versus some other outcome. All of these are active research questions, with current papers being published, data being collected, models being refined. The subject is not closed. And the objects themselves, patient and cooling in the dark, will still be there when we work out the answers. The next time you look up at the night sky and see Sirius blazing at the horizon, or when you find the bright stars in Canis Major on a clear winter night, remember that just a few arc-seconds away from that brilliant star is its companion, a body the size of Earth, containing the mass of the Sun, held together by the Pauli exclusion principle. Cooling toward a final cold state, it will not reach for trillions of years. An archive of a stellar life, written in degenerate matter and crystallizing slowly under gravity. Still warm, still radiating, still there. The physics inside a white dwarf stops behaving normally the moment you understand it. Because once you understand it, the universe stops looking the same. There is one aspect of white dwarf research that has emerged in the last decade and that reshapes how we think about the connection between dead stars and living worlds. The planetary debris accreting onto white dwarfs is not just rocky material. In some cases, the composition analysis suggests the accreted bodies contained significant amounts of water. Oxygen in white dwarf atmospheres, in excess of what you'd expect from silicon oxide minerals, is the signature. When you see more oxygen than can be accounted for by the rocky minerals, the excess likely came from water ice in the accreted body. Water-rich bodies orbiting white dwarfs. This has profound implications. It means that the delivery of water to rocky planetary surfaces, the process thought to have brought much of Earth's oceans from water-rich asteroids in the outer solar system, appears to happen in other stellar systems too. It means that water is a common ingredient in rocky planetary systems across the galaxy. And it means that the conditions that might allow liquid water to persist on a rocky planet, the presence of water to begin with, are not unique to our solar system. Some of those water-bearing bodies accreting onto white dwarfs today are fragments of what were once water-rich asteroids, or perhaps even the remnants of former ocean-bearing worlds. Disrupted and shredded as the planetary system around the dying star was disturbed by the dramatic final phases of stellar evolution. Reading white dwarf atmospheres is reading the chemical inventory of planetary systems around other stars. And what we're reading suggests that the ingredients for habitable worlds are common. The raw materials are spread broadly. How often they assemble into something complex enough to look up at the stars and wonder about them is a different question. But the ingredients are there, written in the spectra of dead stars. The cooling sequence of white dwarfs, visible as a clear track in temperature-luminosity diagrams, is one of the most used tools in observational astrophysics. Star clusters are particularly useful here. When a cluster forms, all the stars in it form at roughly the same time from the same cloud of gas. They have the same age, though different masses. The most massive stars evolve fastest and leave the main sequence first. Over time, progressively less massive stars finish their evolution and become white dwarfs. The white dwarfs in an old cluster are all cooling and fading, but the most recently formed ones are brightest. The oldest formed ones are faintest. By mapping the distribution of white dwarfs in a cluster along their cooling sequence, and matching that distribution to theoretical cooling models, astronomers can determine the age of the cluster with considerable precision. Older clusters have a shorter, fainter, white dwarf cooling sequence because the oldest white dwarfs have cooled beyond the detection limit. Younger clusters have a longer, brighter sequence because fewer white dwarfs have formed and they haven't had as long to cool. This technique, white dwarf cooling age dating, has been applied to dozens of clusters. The oldest globular clusters, the ancient spherical collections of hundreds of thousands of stars that orbit the halo of the Milky Way, have white dwarf cooling ages consistent with ages of around 11 to 13 billion years. These are among the oldest objects we can directly age date in the universe. Their ages set a lower limit on the age of the universe itself. The universe must be at least as old as its oldest stellar populations. And those stellar populations have white dwarfs whose cooling ages confirm what we find from other methods. The universe is old. The Milky Way is almost as old as the universe. And the white dwarfs in its oldest clusters have been cooling since before our solar system existed, since before Earth was born, since before any of the atoms in your body were assembled into molecules, let alone into living cells. They were cooling then. They're still cooling now. The universe is not finished telling this story. Every white dwarf catalogued, every spectrum analyzed, every pulsation mode measured adds another data point. The population grows as surveys improve. The physics sharpens as models refine. The surprises continue because nature at extremes is more complex than our initial models anticipate. That's how it usually goes. The more carefully you look, the more you find. White dwarfs have been rewarding careful attention for over 100 years, ever since Friedrich Bessel noticed Sirius wasn't moving in a straight line. They'll keep rewarding it. The Pauli exclusion principle has been holding them up for billions of years. It will keep holding them up while we keep studying them. One question at a time. one observation at a time. One step further into the physics of matter at the edge of what physics allows. Good night.